When we want to describe the motion of objects that have size, that don't exist at a single point, but have size and can rotate, the center of mass is the location that we can treat as the center of the object. Now we've heard a little bit about the center of mass and the center of mass velocity already, but let's take this video to make it concrete. First, I'll consider how to calculate the center of mass for a collection of point particles. So we imagine a collection of objects that themselves don't have any size, but have distinct masses, m1, m2, m3, and distinct x and y coordinates, x3, y3, x2, y2, and x1, y1. To calculate the total mass of this system, our notation is just to sum up the mass of each object. Then the center of mass is determined as a weighted average of the positions of each piece, weighted by their mass. In the same notation, we would sum over all of the particles in the collection, the quantity, the mass of that particle, times its x-coordinate, and after getting that sum, we would divide by the total mass. This would give us the x-coordinate of the center of mass. To get the y-coordinate of the center of mass, we would do the same thing, except adding up the masses times the y-coordinates of the individual pieces. So being a weighted average, we expect that the center of mass will be somewhere around the geometric center of the collection of objects, but closer to the parts that have larger mass. Now, the collection of point objects treated as one thing is somewhat abstract, but these formulas can be generalized to give us a way to get the center of mass of any object or any collection of objects. But first, let's do an example where we actually do have a collection of point objects and just see how the center of mass works out. We'll need to know the coordinates of each piece or each point and its mass. Let's set up a system where there is 100 gram mass at the origin, at the x-coordinate 4 centimeters and the y-coordinate 3 centimeters. There's a second mass in the system with 70 grams. And at the x-coordinate of 3 centimeters, y-coordinate of 1 centimeters, we'll have a mass of 50 grams. So we might describe this system by saying m1 equals 100 grams. Position 1 is 0, 0. m2 is 50 grams. Position 2 is 3, 1 in centimeter units. m3, 70 grams, and r3 is 4, 3 in centimeter units. That would describe the collection of objects. First, let's calculate the total mass. This will just be the sum of all the masses in the collection. So 100 plus 50 plus 70 gives me 220 grams. For the x-coordinate of the center of mass, we will take the sum of m1 and the x-coordinate of r1. So 100 grams times 0 centimeters. Same term for m2, 50 grams times 3 centimeters. And the same term for m3, 70 grams times 4 centimeters. That sum is then divided by 220 grams, which is the total mass. And the result is 1.954 centimeters. For the y-coordinate of the center of mass, we would do the same type of sum. With the same masses, but now with the y-coordinates. The y-coordinate of mass 1 is still 0. The y-coordinate of mass 2 is 1 centimeter. And the y-coordinate of mass 3 is 3 centimeters. The result of this calculation is 1.182 centimeters. So the center of mass of this collection of 3 objects is at 1.954 in x and 1.182 in y. It's a definite location in space that exists as a property of this collection of objects. As long as this set of objects remains rigid, doesn't change their relative positions, the center of mass will always be at this location relative to the set of objects. Now, a collection of point particles might seem a little bit artificial, but we can use this to good effect by adding in the following principle. If we consider a single object that has a continuous distribution of mass, such as a plate, a disk, a rectangle, anything that's made of a solid, and that object has some symmetry, like a rectangle has a line through its center about which it is symmetric. A circle can be rotated around its center, which is a rotational symmetry. So let's write this out. A continuous object of constant density has its center of mass at its geometric center. So, for example, a disk, sphere, circle, the center of mass would be at the center of the circle. That's a geometric point that's at the center. If we have something like a rectangle, the center of the rectangle geometrically is halfway from either edge vertically and halfway from either edge horizontally. So that is the center point there. If we have a different shape, which we're not so familiar with, we can always find geometric center by looking for lines of symmetry. So here I've got an isosceles triangle. It has one line of symmetry, a line of reflection symmetry straight down its center. So if I were to reflect this object across this line, it would stay the same. So we know that the center of mass, or the geometric center of this isosceles triangle, must lie somewhere along the line of symmetry. What we don't know is how vertical the center of mass, or geometric center is. But we do know it's along this line. For the rectangle, a line of symmetry would be here, vertically dividing it, here, horizontally dividing it. And those must be, those lines must have the center, the geometric center somewhere on them, so where they cross, that must be the geometric center of the object. So that's one principle. If we just have a continuous object with a simple shape, we can find its center of mass by looking for its geometric center. Now the second part of this which lets us apply this point particles thing to continuous objects, is that a continuous object acts as a point particle. For center of mass calculations, with all of its mass at its center of mass. So if we have some sort of circle, and the circle has a total mass of, say, 10 kilograms, and we know the coordinates of its center, then for calculating the center of mass, if this circle is just a part of a larger object, then we can treat this circle as if there is a point object at its center of mass that holds a total mass of 10 kilograms. So the size and extent of the circle don't matter anymore towards its contribution to the overall object. We can reduce a continuous object to a single mass sitting at its center. So let's apply that now to another example with some continuous objects. So let's have a rectangle and a disk. Shown here. So, not actually a rectangle, we're going to use a square. A square is also a rectangle, but we'll be more specific. So the square, we use 20 centimeters long and 20 centimeters tall for the square. And we'll let the square be called object 1 if we want, and give it a total mass of 800 grams. Now next to the square, sitting tangent to it, we will draw a disk. This is the disk. And the disk will have a radius, we'll set it up to be 8 centimeters and a mass of 400 grams. And our task here in this example is to find the center of mass of this collection of two objects. These could be like parts of a machine or something. We need to find their center of mass in total. So based on the principles that we just discussed, we can break both of these objects down into point particles with their centers holding all of the mass. So for our rectangle, its x coordinate of its center is halfway from either edge horizontally, so 10 centimeters. And for its y center, it's again 10 centimeters, so halfway from the bottom to the top. For the disk, its center of mass is at its geometric center, but that's not, this is not directly touching the axis over here. So to get to the center of mass in terms of the x-coordinate, we have to go over 20 units, and then we have to go over one radius of distance. So the x-coordinate of the center of mass for the disk is 28 centimeters. The y-coordinate for the center of mass of the disk is just up 8 from the x-axis, so 8 centimeters there. So once we do that, then we can just imagine that there's a point particle at this location of mass 800 grams, a point particle at this location of mass 400 grams, and calculate the center of mass like that. So what we will get for the x center of mass of this combined object is we'll write it out. It'll be 1 over 1,200 grams is the total mass. We have 800 grams times 10 centimeters plus 400 grams times 28 centimeters. And that calculation gives us, in the end, 16 centimeters for the x-coordinate of the center of mass. If we follow through it and do the same thing for the y-coordinate, you can test yourself with this calculation. The answer is 9.33 centimeters. So the center of mass of this system, this is 20 along here, this is 28, that's 10. So 16 is just about there for centimeters horizontally. 9.33 centimeters is, well, the middle of the square is at 10, so 9 is a little bit less than that. So this spot here is the center of mass of the collection of square and disk. And as we expected, it's kind of an average position of both of them, a little bit closer to the center of the object that's heavier. One additional thing that you can deduce from these formulas is that if you have just two objects that you're putting together, the center of mass will always lie along a line that joins their centers. Since it's a weighted average of two locations, two position vectors, it is linear in the position vectors, so it can only form a line between them based on their proportion of masses. Right, so that's where we see this center of mass showing up in the square and disk example. Now, how do we approach an object that is not a simple shape? So a triangle that is not isosceles, a semicircle, something that it doesn't have enough lines of symmetry to identify the geometric center. Well, then we need to generalize our formula for point particles and make the points in such a way that they build up the object piece by piece. So our sum, say for mass first, we'll change our small bits of mass mi into infinitesimal bits dm and add them all up in an integration procedure. So we'll integrate over the entire object of dm, and that will give us the total mass. For our summation for the x-coordinate of the center of mass, we'll still divide by the total mass. Our summation, we'll send the size of the chunks of mass to an infinitesimal amount. And the x-coordinate of each piece will still be relevant, so it will stay in there. So we'll integrate x dm over the whole object and then divide by the total mass to get the center of mass of the y-coordinate, x-coordinate. And then I won't write out both ways of looking at it. For y, it's going to reduce down to just the integral of y dm over the whole object divided by the total mass. So this is similar to calculating, say, the way we have to set up these integrals is similar to what we did for moment of inertia, actually. We have to think about three things. How is dm related to positions in the object? We'll need to maybe think about concepts of density. Secondly, how is the boundaries of the object described? What are the limits on this integration? Integrating integral over dm is, hopelessly vague. We need to put some boundaries on this, a top and a bottom, a left and a right, that sort of thing. And thirdly, how do we do these integrals? If we're talking about one-dimensional, we have one integral. Two-dimensional, we have a double integral. If it's a volume solid, then we have a three-dimensional integral to carry out. So let's go through these issues with a concrete example. I'm going to calculate the center of mass of an object that doesn't have any obvious lines of symmetry. So it's a triangular flat shape, so we're still working in two-dimensional coordinates here. And I'm thinking of a right triangle with a base of 4 centimeters wide, a height of 3 centimeters tall. And we'll give this triangle a constant density of 20 grams per square centimeter. So it's in 2 dimensions, grams per square centimeter. Okay, let's move these over. Okay, so the first thing we have to work out is how the dm is related to the distribution of mass in this object. This object has a constant mass density, so that's kind of favorable here. And we can express the boundaries of this object in terms of x and y coordinates. So our small area on the object will have an area of dx dy. The density at that point is a constant. We'll call it sigma. It's equal to that 20 grams per square centimeter. And so that's our expression for dm. The dm is the amount of mass in a little infinitesimal chunk. All right? So that's what we're going to use for dm, and it tells us that we're going to need to talk about x and y limits on our integrals. We'll have a double integral. So then our next step is to think about those limits. For x, it's pretty simple. We can just say x goes from 0 to 4 centimeters. But what about y? Y doesn't go from 0 to 3 for all x coordinates, right? It only goes from 0 to 3 when x is equal to 4. When x is equal to 0, the y doesn't even change. So we need to think about the boundaries on y. So y is always above 0. But depending on the x coordinate in the integrand, the y value will not go all the way up to 3. It will go to basically this line. So this line here that forms the hypotenuse of the triangle is a line of 0 intercept and slope of 3/4. The y equals 3/4 x is the equation of this boundary, the top. So y will go from 0 up to 3/4 of x at a given x value. So that's going to be our limits on integration. We'll put the x integral outside to the left and the y integral inside because its limits will depend on x. Okay, so now all that's left to do is actually set up the integrals and do the math. So we'll do maths first because this will be a good test and it will give us a way to check if we've got this stuff set up right because we'll get an expected result. All right, so for x, I'll go from 0 to 4. From y, I'll go from 0 to 3 over 4 times x. Then my integrand for mass is just sigma. Okay, so sigma is a constant. I can pull that out front. I'm going to get 20 grams per centimeter squared. I'll leave the x integration alone for now. I've got to do this y integral first that's on the inside. So I'm integrating dy, like the integrand is basically 1 here, so the antiderivative is just y, and it's evaluated at 3 over 4x minus evaluated at 0. So I'll have 3 over 4x. This is the result of my y integration. The next step, I'm going to do the x integration. Let me write it out here carefully. The 20 is still out front. The 3 over 4 is a constant, which I can leave up front for later. And then my integral is x is the integrand, dx is the integration variable, so that's going to be an antiderivative of x squared over 2 using the power rule. So I'll have 4 squared over 2 minus 0 squared over 2. So we'll get here 4 centimeters squared divided by 2. All right, and that's the formula then for the total mass of this triangle. Let's look at what's going on here, though. We have 20 grams per centimeter squared. We've got a 3/4, and then we have 4 centimeters times 4 centimeters. So basically, if you look at this formula for a bit, you can convince yourself that this is basically equal to the area of the triangle multiplied by its density per area. So 3, this 4 can cancel one of those 4s. You'll have 1/2, base is 4 centimeters, height is 3. So you get the area of the triangle. So that worked out. All of our setup for limits and our setup for density worked. So when we actually plug in these numbers and calculate it, it will come out to 120 grams. Right. It's always good to do it first. You need to know this so that you can divide by mass in these other ones. Once we've got the integral for mass figured out, the integrals for x and y are very easy to set up. Just a little bit more work to do them because you have more things in your integration. So I'll write out what these are. That's a 3/4x, 3/4 times x dy. And then the integrand here is sigma times x for xcm. What does that mean for doing the integral? Well, I can pull the sigma out front, that's still constant. My total mass is out front, that's outside anyway. When I do the integral over y, I will get that 3/4 times x that I got before. Then there's another x sitting here because we're doing the x coordinate of the center of mass. So when I do this integral, I'm going to have an integrand of x squared dx, and my antiderivative will be x cubed over 3. So let's write everything in here. 20 grams per centimeter squared divided by 120 grams for the total mass, times this fraction of 3/4 from there. And then I'm going to have my 4 centimeters cubed over 3 from the x integration. Okay, so when everything is plugged into there, we get an x center of mass that is 2.67 centimeters. Setting up the integration for this for the y coordinate of the center of mass is almost the same as this, except our x here turns into a y. I will let you take it as a point of practice to see if you can work out the y center of mass on your own, and you can check after you do that. If you get the correct answer, it is 1 centimeter. So when we look at this triangle for its center of mass, our calculation says that it is 2.6 centimeters in x and 1 centimeter in y. So right about there where I drew my little bit of dy before. All right, so it's always good to just look at these numbers when you're done with the calculation and think, well, is that kind of in the middle of the object? Well, yeah, more or less it's kind of in the middle. And that makes sense. So that's how we find the center of mass of a continuous object that has some mass distribution over some region of space. Now, the same technique can be applied if the density depends on x or y. That will just get plugged in here. You'll have more to do with your antiderivative. You might need to look in a table or something. And it also works out exactly the same if you have a 3-dimensional object. These integrals turn into volume integrals. You have an x, a y, and a z limit, and that's how it works in 3D. So there's not a lot different about those scaling up to more dimensions. Last thing I'll give you here, just to make things efficient for you, is if you have a shape which is maybe set up in terms, maybe easier to describe in terms of polar coordinates. So something like a semicircle. Now you could describe a semicircle because the y coordinate of the top can be deduced from Pythagorean theorem, and the x coordinate goes from, say, minus r to plus r, and it would be very similar to these. You just have a different upper limit for your y integration based on the y coordinate of this curve. Then you'd be doing integrals involving square roots and stuff like that. But if you have a shape that is much easier to describe in terms of polar coordinates, you can set up your integration in terms of polar coordinates, where your dm would then be the density times your area, your small bit of area, right? And for polar coordinates, if you're looking at a given increment of angle, theta, and a given increment of radial distance, dr, this will be dr times r d theta. Right, so for this mass integral, I might set it up like this. Well, I'm going to integrate from 0 to capital R for dr, from 0 to pi, just because it's only a semicircle, for r d theta, and then my mass density sigma, whatever that is, would come in there. All right, so that's how to set up these integrals if it's more convenient to do so in polar coordinates. And again, if you did this, we would expect to get, say, density times area if the density was constant. Like density times pi r squared over 2 would be the outcome of this integration if I treated sigma as a constant. Okay, so that's our discussion of center of mass. In summary, we've got 3 things that we should be able to do with this. If we have a collection of point particles, we can calculate the center of mass of those. By a weighted average procedure. If we have a collection of known shapes, we also do the same thing using the x or y coordinate of their centers. So we use center of mass of each shape. So the shapes might be simple things like circles or rectangles, where you can just guess the center of mass by looking for their center. Or they could be things like semicircles or triangles, where you already figured out the center of mass from an integral calculation, then you can just use that as the center of mass if it's only a small part of a bigger situation. And then the third thing we'll know how to do is calculate the center of mass for a, we'll call it an asymmetric continuous object. Using the method of integration that we just went through for the triangle.